Hello Year 11, it's Miss Bailey here. So hopefully you've already seen the starter on the Padlet, so that was to self-mark your chromatography questions from last lesson. So it's really useful for you to be able to see what the examiners have put in mark schemes so that you know the keywords that they are looking for. So in today's lesson we're going to be looking at how we can use different tests in order to identify particular gases. Please have the worksheet that's on the Padlet ready so that we can be filling this in as we go through this lesson. So to start with, we're going to think about the gases that we're going to be looking at. So this is showing you a dot and cross diagram for chlorine, which is a diatomic molecule. So di means two, so chlorine existing as a molecule with two atoms bonded together. So using our periodic table, we can see that chlorine is in group 7. And so each chlorine atom has 7 electrons in its outer shell. So the two chlorine atoms join together in order for them to have a full outer shell, as that will make them more stable. So what happens is they share that 7th electron with each other. So it's a covalent bond. The co meaning shared, and the valent referring to the outer electrons. So they are sharing those two outer electrons, and so if we count up how many electrons each atom has available to it, they both now have access to 8 electrons, and so they have this full outer shell. So by forming a diatomic molecule, chlorine is more stable because it has shared its electrons with another atom. So applying these principles and using your periodic table to identify what groups each of the atoms have come from, I will just write the chemical formulas there for you. So hydrogen is H2, oxygen O2, and carbon dioxide is CO2. Can you pause the video and have a go at drawing similar diagrams, so dot and cross diagrams, for hydrogen, oxygen, and carbon dioxide? Okay, so oxygen has a double bond. So because oxygen is in group 6, it needs 2 electrons in order to have 8, and so it actually shares 2 of its electrons with the other atom. So you can see 2 crosses and 2 dots. So each oxygen atom has shared 2 electrons, meaning there are 4 electrons in total that are used in this covalent bond. And so this is actually a double bond, where one bond is one pair and the second bond is the other pair. And we also see double bonds with our carbon dioxide. So we can ignore the inner shell, but focusing on our outer shell. So carbon is in group 4, and we've seen that oxygen is in group 6. So carbon needs access to 4 electrons, whereas each oxygen needs access to 2 electrons. And carbon has 4 electrons to start with, and so the way in which it gets those 4 electrons is 2 from each oxygen. So you can see here we've had 2 circles from our oxygen, and again here 2 circles from our oxygen, and we've used the 4 crosses from carbon to be sharing those with the oxygen. So this oxygen shares those 2 crosses, and this oxygen shares those 2 crosses. And if we count the outer shells, we will see that they each add up to 8. So again, utilising double bonds. With hydrogen though, now hydrogen only has that first inner shell, and our inner shell can only actually hold 2 electrons. And so hydrogen being in group 1 it has one electron, but it also needs just one electron in order to make it full. And so by sharing its electron with another hydrogen atom, which shares its electron with the first one, we then form a covalent bond between those two hydrogen atoms. But you can see when you count the number of electrons each hydrogen has access to, they both have access to those two electrons and therefore have that full outer shell, making it stable. So a couple of lessons ago we looked at how to use Freya models to help with our definitions of terms. So can you have a go at completing this Freya model for the term diatomic? So pause the video whilst you have a go at this. Okay, so there are two videos for you to watch in order to see how we carry out these different experiments to test for these four gases that we've just been looking at. So on your worksheet there is a table for you to fill in, listing the experiment from the video, the positive result, so by that we mean what happens in that experiment to confirm that it was that gas present, and then for the reason for the result. We have four choices for you to consider, for you to be able to match those up to the relevant gas that's being tested. Some of those will be explained in the video, some of those you might need to draw on your own knowledge for in order to complete that table. So, question for you to consider: which gas has been produced here? If we're testing for using our litmus paper, and we can see there, tip of it has gone white. And why we don't do this in an open school lab, so even if we were doing face-to-face teaching, we wouldn't typically do this in a lab because chlorine can be very toxic. So the gaseous fumes of chlorine is toxic and therefore it wouldn't be safe for us to do. So thinking about different reactions that you will have looked at last year, such as metal and acid, metal carbonate and acid, and use of a catalyst in that hydrogen peroxide decomposition. What is going to be the gas that's produced in each of those examples, and therefore which of these tests is going to give a positive result. So we should only have one tick in each of those rows and then two crosses in each of those rows. So pause the video whilst you have a go at those. So zinc and hydrochloric acid, so this is a metal plus acid reaction, and so we end up producing hydrogen gas, and therefore we're expecting it to ignite with a squeaky plop when we present it with a lit splint. Our hydrogen peroxide, use of a catalyst, this decomposes our hydrogen peroxide into oxygen and water, and so here we would expect it to relight a glowing splint because our oxygen gas completes the fire triangle and therefore relights it. With calcium carbonate and hydrochloric acid, so we end up producing a salt, water and carbon dioxide gas, and so we would expect a positive result when we test it using lime water. Thank you all for watching and see you next time.